And you may
Okay,
start.
in my report, I will present the research result devoted to the restoring the properties of heat-resistant steel after its long-term use on the steam pipeline bands of thermal power plants using heat treatment. Outline of the presentation is the following: introduction, the object of research, methods, results and discussion, as well as conclusions. The operational efficiency of the main steam pipeline at thermal power plants is reduced due to several factors, including operating temperature, pressure, duration of operation, and the frequency of process shutdowns. All these factors contribute to the degradation of heat-resistant steel of the main steam pipeline. It is well known that long-term operation of low alloy heat-resistant steel under elevated temperature and loads is accompanied by creep, which changes their microstructure. Hydrogen further accelerates the degradation processes of these steels. Structural phase transformation of these steels are associated with the precipitation and coalescence of carbides, and an increase in grain size significantly affected the reduction of its properties. Due to the mismatch in elastic moduli and thermal expansion of coefficients between the large carbides and the matrix, the bond between them weakens. This facilitates their decohesion and the formation of voids around them. Chains of voids along the grain boundaries become energetically favorable sites for hydrogen, absorbed by steel during the operation. These voids are more easily combined into microcracks in the presence of hydrogen in the metal. This reduces the steel's mechanical properties and accelerates the structural element fracture. Restorative heat treatment is already used to improve the microstructure and mechanical properties of previously used steels. In particular, to restore the properties of heat-resistant steel after its long-term use in the fastening elements of the high-pressure casting of TPP steam turbine. Repeated heat treatment was applied according to the general accepted industry regime. It is use made it possible to significantly reduce the size of carbides in structure of 25H-M1F steel and slightly increase its hardness, strength, ductility, as well as significantly increase impact toughness. In this work, the experience of using restorative heat treatment was extended to the main steam pipelines of thermal power plants, in particular to sections of their bands. Damage over 90% of steam pipelines bands occurs in their stretch zones from the side of the outer surface of the pipe. One of the reasons for their appearance is the smaller cross-sectional of this zone, due to the peculiarities in the band manufacturing process. The purpose of the work is to substantiate the feasibility of using heat treatment to restore the structure and mechanical properties of non-housed MF steel after long-term operation in the strange band zone of the main steam pipeline of a thermal power plant. The chemical composition of the studied steel is presented in the table. The analysis of the structural and mechanical state of steel used in bending steam pipelines was carried out at 3 levels along the pipe wall thickness, near the outer surface, the inner surface, and in the center of the pipe section. Mechanical tests were carried out on tangential-oriented samples. The orientation of the fracture surface of the impact toughness tested specimen corresponded to the orientation of the axial damage surface in the operated bands. To assess the actual state of operated metal, the following characteristics were used: hardness, ultimate tensile strength, yield strength, elongation and reduction of area, and impact toughness. The testing equipment and the specimen geometry are shown on this slide. Also, a scanning electron microscope EVO 40 XVP was used for metallographic and fractographic studies. The research is devoted to the substantiation of the restorative heat treatment mode to improve the structure and mechanical properties of operated steel. The tests were carried out on the tangential templates taken from the stretch zone of bending of steam pipeline of the main steam pipelines after 286,000 hours of operation at 540 degrees Celsius and a steam pressure of 14 megapascals. The first stage of template normalization was carried out at a temperature of 1100 degrees, with the different holding times varied from 300 to 630 minutes. It was expected that the carbide that formed during long-term operational would dissolve during the first stage of normalization. This should be accompanied by homogenization of the solid solution and the disappearance of small voids. During the second stage of the heat treatment, the specimens were normalized at lower temperature of 960 degrees and tempered at 740 degrees according to the regime recommended for such steels in initial state. The grain and inclusion size in the steel structure were evaluated for the operated steel and after each of the applied heat treatment regimes. Structural changes near the outer and inner surfaces of the pipe and in the center of the pipe section were analyzed. For quantitative analysis of the grain were conditionally divided into three categories: small, up to 10 micrometers, medium, from 10 to 30, and large, over 30 micrometers. The relative number of grains of three categories observed in the structure of steel from strange zone of bend and after long-term service at various stages of normalization or after optimal restorative heat treatment mode are shown on this slide. It was found that after 30 minutes at 1100 degrees, the proportion of large grains in the steel near the outer surface of the pipe decreased to 35% compared to 48%. After the operation, the proportion of small grains at all levels increased from 9-12% to 20-23%. After 150 minutes, the proportion of large grains decreased to 20-25%. The proportion of small grains increased to 30-35%, and medium grains to 40-45%. With holding times of 330 and 630 minutes, grain size changes slowed. Their distribution stabilized. Therefore, during the first stage of normalization, it was concluded that the holding time of 150 minutes is sufficient for homogenization of the solid solution. The second stage of thermal restoration included renormalization at 960 degrees with a holding time of 30 minutes, followed by high temperature tempering at 740 degrees for 180 minutes. This process resulted in the final grain size distribution, consists of 50-55% small grains, 35 medium grains, and less than 10% of large grains. It was considered that this grain size distribution would improve the mechanical properties of the restored steels. The next slide illustrates a relative number of grains of three size categories observed in the structure of steel from strange zone of bend after the long-term operation and after optimal mode of restorative heat treatment. For operated steel, a noticeable grain coarsening was observed, whereas after restorative heat treatment, the proportion of large grains significantly decreased, while the proportion of small grains increased. Moreover, this is a typical regularity for all levels of analysis of the pipe wall thickness. The next slide illustrates the typical steel structure after operation and after restorative heat treatment. As a result of treatment, carbides dissolve and the solid solution is homogenized, leading to a reduction in carbides, especially at the grain boundaries. The heat treatment also promotes the healing of small voids and reduces the number of large voids at the grain boundaries because due to the completion of steel recrystallization, they are located inside the newly formed grains. The next slide illustrates changes in microstructure of steel along the wall thickness of pipes in strange zone of bends after operation and subsequent restorative heat treatment. The degradation of steel structure during long-term high-temperature operation is caused by the reduction of carbon and alloying elements, which transform with ferrite perlite structure into ferrite carbide. The creep in the steam pipelines must lead to the appearance and accumulation of damage, such as formation of voids along the grain boundaries due to carbide decohesion from the matrix or their traces, thereby degrading the mechanical properties of the metal. However, after restorative heat treatment, due to the complete recrystallization of steel structure, unhealed voids on large inclusion, which lost the cohesion of on matrix during operation and relocated inside the grains. Therefore, their role in the process of creep involving the boundaries of newly formed grains by heat treatment will be secondary. The number of carbides of 3 different sizes per unit area of microstructure, images of steel in the strange zone of pipe bands after operational and subsequent restorative heat treatment was analyzed. The number of voids within the grain body and the grain boundaries in the structure of the operated steel and after restorative heat treatment were categorized separately. It was found that at all 3 levels in the pipe wall cross-section, after heat treatment, the number of large carbides with voids around them within the grain body increased, while the numbers at the grain boundaries significantly decreased. The hardness of heat-resistant steel is considered one of the determining indicators of their serviceability. It is evident that after heat treatment, the hardness increased to 170 HB compared to 120, 130 HB for the operated steel. This increase in hardness is in good agreement with the increase in the number of small grains. Thus, as a result of thermal restoration, both structural characteristic and hardness improved significantly. An increase in the strength, ductility, and impact toughness of heat-resistant steel is in the strange zone of the main steam pipeline band after restorative heat treatment, according to the proposed regime, was detected. Since restorative heat treatment improved the structure and key properties of steel, it provides ground to expect that its particular practical application will extend the service life of the steam pipeline components. To assess the effect of hydrogenation on the stability of steel properties after restorative heat treatment, tensile tests in the air were carried out on the smooth samples of both steel variants after their preliminary electrolytic hydrogenation. It was found that the hydrogenation of operated steel worsened its strength and plastic properties. The characteristic of restored steel, although somewhat worsened due to the presence of hydrogen in the metal, remained higher than the values regulated by the industry document for steel in the original state. Fractographically, cleavage areas in the background of ductile relief were detected at the fractures of both variants of hydrogenation specimen. In the restored steel, they were found out only near a large non-metallic inclusion, whereas in the operated steel, their number was significantly greater due to the large numbers of pores along the grain boundaries, in which hydrogen could accumulate, facilitating the formation of cleavage. Thus, the improvement in the structure and mechanical properties of heat-resistant steel established for restored steel provides the prospect of using proposed mode of heat treatment to extend the service life of steam pipeline bands in thermal power plants. The last slide presents the conclusion drawn from our research. I am a PhD student and the work is being carried out under the supervision of Helena Krychkowska. Thank you for your attention.